Alright, welcome back to Quite Basic Math. Now we'll be rounding off complex numbers for QBM 101, which is a basic idea of complex numbers with these worked examples. By the time you go further, probably in QBM 201, we'll still review complex numbers, but we'll just go a step further, and then we'll be able to tackle much more, or we'll be able to tackle things that are even difficult, more complex and advanced than this. But for now, we'll be climaxing here. So let's solve these four worked examples. You can pause the video and try to solve this yourself to see if you really can give it a shot. Okay, I'll be solving them now. Let's start with the first one. Now we have to evaluate the imaginary part of the complex number I raised to the power of 111. I think that's 1 in 5 places. 11111. Now the drill, don't forget the drill of higher powers. We said that this can be broken into factor of 4. Once you can divide 11111 by 4, that would make the work very easy to solve. Okay, so let's see how we can do that very quickly. Let's see how we can do that very quickly. Now if you punch your calculator to try 11111 divided by 4, you get 2, if I'm not mistaken, 2777 whole number 3/4. This is what you get, right? Or 2777.75. Now what you want to do is, what you're interested in is the remainder. Don't forget. Now your remainder is what you have here, which is 3. You know, this is the same thing as saying 4 times 2777 plus 3. The remainder is what you're after. Now this part, you can split this to I raised to the power 4 into 2777 times I raised to the power 3. That's the drill. And this would give us 1. So that's 1 times I raised to the power 3. We already know that to be minus I. So basically, this is I raised to the power 1 in 5 places is just minus I. Now for us to now evaluate the imaginary part of I raised to the power 11111 is simply the imaginary part of minus I. And the imaginary part of minus I is simply -1. Don't forget that we said that if you have a complex number z, that is x plus iy, the imaginary part is simply the coefficient of I in the complex number, which is y. So in this case, coefficient of I here is -1. So that's how we know that the imaginary part of I raised to the power 11111 is -1. Alright, let's move on. Now for the second question, the same procedure applies again. You have I to the power of n plus 111 plus I to the power of n plus 1 or plus 222 plus I to the power of n plus 333 plus I to the power of n plus 444 plus I to the power of n plus 2356. Break every one of these powers. Now you would have I raised to the power n times I raised to the power 111 plus I raised to the power n times I raised to the power 222 plus I raised to the power n dot I raised to the power 333 plus I raised to the power n dot I raised to the power 444 plus I raised to the power n dot I raised to the power 2356. The law of indices guides that. Now the next thing to do to simplify is that I can factorize I raised to the power n, right? And then I have I raised to the power 111 plus I raised to the power 222 plus I to the power of 333 plus I to the power of 444 plus I to the power of 2356. Now this is I raised to the power n into, now I raised to the power 111, don't forget the drill. Just divide 111 by 4. Once you do that, you should get 27.75, just like this case here. So that will just be I raised to the power 4 times 27, okay, times I raised to the power of 3, just like what you have here, plus I raised to the power 222. Do the same. Divide 222 by 4. You get 55.5. And 55.5 is the same thing as 55 1 over 2. So that will simply be now for us to get something that we want that includes 4, you have to look for the closest number to 222 that you can divide 4 with. What I mean is 4 times what will give you 222, the closest, that will give you something close to 222. Now if you do 4 times 50, you get 200. 4 times 51 is 204. You can try 4 times 55, which is 220. So you have I to the power of 4 times 55, okay, times what you have left. Since this is 220, will just be I squared, all right, plus then I is power 333. Divide 333 by 4. Does it give you okay, it gives you 0.25. Now if it gives you 0.25, don't forget 0.25 is the same thing as what I mean is divide 333 by 4, and you'd have 83.25, which is 81 over 4, and this is the same thing as 83 times 4 plus 1, right, over 4. I believe you understand what I'm saying here. So that will give us I to the power of 83 times 4 dot I, okay, because 83 times 4 is 332, so plus 1 is 333. Okay, and finally, okay, we're not done. Then I is power 444. You agree that that's just 4 times 111. That one is straightforward, which is just 1. Then plus for 2356, you do 2356 divided by 4. That one too is straightforward. That will be I to the power of 4 times 589. Okay, then you close your general bracket. Then from here now, let's evaluate easily. This will be I raised to the power n into, this is 1 times this I cube plus I squared plus I plus this is 1 plus 1. Okay, now this is equals to I to the power of n into I cube is minus I squared is minus 1, then plus I plus 2. Okay, I mean 1 plus 1 minus I plus I, that's 0. The minus 1 plus 2, that's 1. So that's I raised to the power n times 1. So this implies that your answer would simply be I raised to the power n. So the simplification of all these long guys is just I raised to the power n. Okay, I hope you are learning. Now to the third question, the third worked example. Now they said we should find the least possible value of k for which this expression is equal to minus 1. The least possible value of k for which this expression is minus 1. Now before I scroll down, I can do something interesting. And what's that? I can first rationalize this. So this just looks like a single complex number. That will be easier to understand. So just simplify what you have here. Okay, so let's go. That will be 1 plus I over 1 minus I. Let me write 1 plus I over 1 minus I to the power of the square root of k squared plus 1, okay, equals to minus 1. That's the question. So we're looking for the lowest possible value of k for which this expression holds. For which the equation rather holds. So if you rationalize this, you have 1 plus I over 1 minus I. Let's just deal with what is inside so I don't tag all this along. 1 plus I over 1 plus I. Okay, this will be equals to 1 plus 2I plus I squared, okay, over 1 minus I squared. This will be equals to 1 plus 2I minus 1 over 1 plus 1. And this will be 2I over 2, which is equals to I. So everything that you have in this bracket is just I. So that's like saying I to the power of the square root of k squared plus 1 equals to minus 1. So this question is just asking you that what is the lowest possible value of k for which you would have minus 1. When you have I to the power of that k, you will have minus 1. Then you ask yourself, This is very simple. On the right hand side, ask yourself on the right hand side that if what can I raise I to that would give me -1 easily from here? You agree with me that it is 2 I squared. That's the lowest value of the power you can have, meaning that this question can be, this equation can be written as, or rewritten as this. I don't know if you are following me. It can be written as this. I raised power this guy is something as I squared. Since we're looking for the lowest possible value, then from the law of indices we can equate the bases, and then the power will be root k squared plus 1 equals to 2. And what we do from here is you square both sides, right? So this will be k squared plus 1 equals to 4, and this will be k squared equals to 3. So k will be equals to plus or minus square root of 3. But the question asks for the lowest possible value of k. So this implies that the lowest possible value of k will just be negative root 3, and not just root 3. It will be actually negative root 3, because your answer is actually root 3 or minus root 3, but we're looking for the lowest possible value. So your answer will be negative root 3. Now to the last question. Last question is saying that if you have z to be equals to 1 over 1 minus root I, we have to evaluate the modulus of z and the argument of z likewise. Now for us to do that, you must first understand some principle. This denominator you have here is the issue we have. Root minus I is a problem. Why is this a problem? It's a problem because this in itself needs to be resolved. This in itself needs to be evaluated before we can now apply any principle that we need to apply. So you ask yourself, what is root minus I? Okay, root minus I is the same thing as I to the power of half, right? And if I convert I to Euler form is e raised to power I pi over 2. How did I know that? I knew that because this is the same thing as I, just ordinary I. How did I know that? I know that because the modulus of I is 1. The argument of this I is pi over 2. Hope you've not forgotten. And we said the Euler's form is e raised to power I theta. So theta here is pi over 2. Okay, because it does not have a real part, it just have a positive imaginary part. So this from the law of from De Morgan's rule, De Morgan's theorem rather, this will be e raised to power I pi over 4. So root I is the same thing as this guy. So I reformulate my z to be 1 over 1 minus e raised to power I pi over 4, right? And then there's a rule that you should understand as one of the properties of modulus and argument likewise. I already said that the modulus of z, okay, let's say z1 over z2 is the same thing as the modulus of z1 over modulus of z2. Now for argument, there's a principle for argument. And that principle is that if I have the argument of two complex numbers dividing, okay, it's the same thing as the argument of the first one, the numerator, minus the argument of the denominator. Okay, so let's start with modulus anyways. Now we have 1 over 1 minus e raised to power I pi over 4. Now even this is still complex to analyze, so for us to make this easy for ourselves, let's convert e raised to power I pi over 4 to rectangular form. I mean to x plus iy, so it is easier to relate this guy to this one. So e raised to power I pi over 4, that would be for us to convert it to rectangular form, let's convert it to polar form first. Polar form is r, don't forget, cos theta plus I sin theta. Now r is the modulus. The modulus is 1. How did I know? There's just 1 that is behind this. Then theta is pi over 4. That will be cos pi over 4 in radian plus I sin pi over 4. Sin pi over 4 and cos pi over 4 are the same thing, which is 1 over root 2 or root 2 over 2. Root 2 over 2 plus I root 2 over 2. Okay. So if I bring this back to this expression z, it means that we have 1 over 1 minus root 2 over 2 plus I root 2 over 2. Now this implies that my z now is 1 over 1, if I open the bracket here, minus root 2 over 2 minus I root 2 over 2. So this is what I now have. Okay, now I can now find the modulus of this. So where the modulus of z now will be the modulus of 1 over 1 minus root 2 over 2, okay, minus I root 2 over 2. So let's find the modulus of this now. So the modulus of z here will be equals to the modulus of 1, which is just 1, over the modulus of 1 minus root 2 over 2 minus I root 2 over 2. And what's the modulus of 1 is just 1, and the modulus of this, of what you have in denominator, is the square root of 1 minus root 2 over 2 all squared, okay, plus minus root 2 over 2 all squared. So if you punch this on your calculator, you have 1 over, a scientific calculator will do this without stress for you, minus root 2 over 2 all squared plus minus root 2 over 2 all squared. I believe you are punching yours too. So your modulus will be minus 1 point, sorry. Sorry, you can't, your modulus can be minus, that's a mistake, sorry. Must have omitted something somewhere. All squared. Okay, so your modulus will be approximately 1.307. Approximately 1.307. It's decimal. Okay, now let's find our arguments now. The argument of z, don't forget that z now is a fraction, which we had as 1 over 1 minus root 2 over 2, right? Okay, minus I root 2 over 2. So the argument, we apply the rule of arguments. That will be arg1 minus arg1 minus root 2 over 2 minus I root 2 over 2. Okay, so from here, our argument here, the argument of 1, I think I mentioned that if you have a complex number that is positive, that does not have an imaginary part but has a real part, your argument is just 2 pi. Okay, minus, then the argument of this guy here, that will be, since we have 1 minus root 2 over 2, don't forget that 1 minus root 2 over 2, you first confirm if it is positive or negative. 1 minus root 2 over 2 is positive, meaning that your x is greater than 0, and then this one means y is less than 0, and that is the fourth quadrant. So it's just simply arctan. What you have here will just simply be arctan minus root 2 over 2 divided by 1 minus root 2 over 2. So you punch your calculator for that. Make sure you put your angle in radians if you want to work with 2 pi that you have here, okay, and you put your angle in degrees if you want to work with 360. So I will be working with radians, and that will be arctan, okay, arctan minus root 2 over 2 coming down 1 minus root 2 over 2. Okay, so I have 2 pi, sorry, I have 2 pi minus 3 pi over 8. Okay, so my arguments now, argument of z will be equals to 2 pi plus 3 pi over 8. LCM is 8, that's 16 pi plus 3 pi, which is 19 pi over 8. So the argument of the complex number is 19 pi over 8. Alright, or in degrees, degrees, that will be 19 times 180 divided by 8. Okay, that's 427.5 degrees. Let's bring it back within 360. So I can subtract 360 from this guy, and I have 67.5 degrees. This is the principal argument. Okay, at 67.5 degrees, or can have 67.5 divided by 180 to convert it to our radians, so which is basically 3 pi over 8. Okay, so or we could have just done it this way. All right, so the arguments, the modulus of z, where z is 1 over 1 minus root I, the modulus is 1.3, 1.307 or 1.31, and then the argument is 3 pi over 8. I hope you have been able to learn something very well. But let me quickly confirm something. Let me quickly confirm my solution. Arctan. Okay. Let me be sure that there are no mistakes anywhere. You also can go over it. Okay. You also can go over it. Okay. 1.3. And the arguments, that's arg1 minus argument of this, argument of 1 being 1 plus 0I, which is just 2 pi. Okay, minus this is a positive number, negative down right, so yeah, arctan minus 2 over 2 over 1 minus 2 over 2 minus 2 over 2, okay, over 1 minus 2 over 2, so minus 3 pi over 8, okay, plus this, it's that 16. All right, yeah. So I believe this is the correct answer, and if you feel that there should be anything, please let me know in the comment section. So that brings us to the end of complex numbers. I hope you learned something. Make sure you continue learning, and you can please refer this channel to all your friends that might have issues with mathematics generally. I will continually be uploading videos that would help you from different areas in university mathematics. And I hope to see you soon in the next video. Bye for now.